So now that we have studied how to solve the heat equation using Fourier transforms, let us turn to an ordinary differential equation, a very important ordinary differential equation that we subject to Fourier analysis. This equation goes under the name of Aries equation, and it is displayed as equation 4.15 in the slide. Now, Aries studied this equation in connection with certain problems in geometrical optics. What happens near caustics in geometrical optics? This was the concern of Aries, and this work of Aries dates back to 1838, nearly 180 years ago. Now you can look at the treatise of G.N. Watson's treatise on Bessel's function. On page 188, you will see a discussion of this. Before commencing on a detailed account of Aries functions, I'd like to point out a certain historical article on the life of Sir George Biddell Airy. He was an astronomer and a director of the Greenwich Observatory in London. A very interesting account I had read long ago was by the astronomer Patrick Moore, but I am not able to locate the exact article now. Maybe you should try to look for Patrick Moore's account of George Biddell Airy on the internet, if you will. Aries equation is y double prime minus 1/3 xy equal to 0. The factor 1/3 is put there mainly for convenience. Okay, so now let us look at this equation. In this equation, there is no y prime term. That is important. Before taking up Aries equation, let us look at a few useful methods for tackling conditionally convergent improper integrals. A classic example of a conditionally convergent improper integral is displayed in the slide 4.16. It's integral 0 to infinity sin x dx upon x. You should check that this integral diverges if I replace sin x by absolute value of sin x. The value of the integral 4.16 is pi by 2. Well, computing the value of the integral is an entirely different matter. Here we are mainly concerned knowing whether this integral converges or diverges. So let us split the integral into two integrals. Integral from 0 to pi by 2 sin x dx upon x plus integral from 1 to infinity sin x dx upon x. The first piece is the integral of a continuous function on a closed bounded interval, and so it is finite and then nothing more need be said about it. The second piece, integral from 1 to infinity sin x dx upon x. Let's turn to that. Let's denote the integral by I. So I equals integral 1 to infinity sin x dx upon x. What is it? It is limit as r tends to infinity, integral from 1 to r sin x dx upon x. Let us do an integration by parts. Let us write sin x as minus d dx of cos x. The d dx will transfer to the other function, namely 1 upon x. The sign will change and it will become 1 upon x squared cos x dx. Integral from 1 to r with a negative sign. And then there are boundary terms. The boundary terms are cos 1 minus cos r upon r. Cos 1 of course is an innocent constant, and as r tends to infinity, cos r upon r goes to 0. And so now we are left with the integral 1 to infinity cos x dx upon x squared, which clearly converges absolutely. So to deal with conditionally convergent integrals, we try to integrate by parts and deal with the situation. Let us look at one more example. This is called the Fresnel integral. Integral 0 to infinity cos x squared dx. This appears in connection with the theory of Fresnel diffraction in optics. So this time we are looking at lots of things from optics. Well, it is not obvious at all that this integral converges. So first, let us make a change of variables. More precisely, you should go from 0 to r, do the change of variables, and then let r go to infinity. But let me just slur over that technicality for now. So again, integral from 0 to 1 cos of x squared dx is an innocent integral. It's an integral of a continuous function on a closed bounded interval, so nothing more need be said about that. So now we need to deal with integral from 1 to infinity cosine x squared dx. We make the change of variables x squared equal to u or x equal to root u. So dx equals 1 upon 2 root u du. So we get the integral from 1 to infinity cos u du upon 2 root u. How does one deal with this integral j? We imitate the same idea that we did earlier, integrate by parts. Write cos u as d du of sin u and perform the integration by parts, and the derivative will fall on the 1 upon root u. It will become 1 upon u to the power 3 by 2, which evidently converges absolutely. So this integral will converge. As an exercise, show that the integrals I and j do not converge absolutely. They are both conditionally convergent integrals. So this is a preliminary to how to handle conditionally convergent integrals. We have seen two examples which are baby examples. The Aries function will be a slightly more complicated example, but before taking up the complicated example, it's expedient to look at these two easy examples. Now let's get to the Aries equation. The Aries equation is y double prime minus 1/3 xy equal to 0. Now we would like to subject this Aries equation to Fourier transform, but the main question is the following. I have given you a differential equation. How do you know that the solution is a function whose Fourier transform exists? In fact, we are going to see that the solution is actually going to be in the Schwarz class, but that is far from obvious. Another question is that the differential equation is a second order ODE. So it has two linearly independent solutions. So another question is, are both solutions in the Schwarz class? Is only one solution in the Schwarz class? Maybe neither of them is in the Schwarz class. So these are all questions that have to be answered. Now one thing is certain, there is no y prime term in the differential equation. Because there is no y prime term in the differential equation, you must recall the Abel-Liouville formula. What is the formula for the Wronskian of two functions? We have a differential equation y double prime plus pxy prime plus qxy equal to 0 if y1 and y2 are two linearly independent solutions, and if w is the Wronskian, then dw by dx is minus pw, but the p, the middle term, is missing in this differential equation, so w must be a constant. The important thing is, if you take two linearly independent solutions, then this Wronskian is constant, and this constant must be a non-zero constant because they are linearly independent. Now suppose if you know that one of the solutions is in the Schwarz class, that it is, it decays at infinity, its derivative also decays at infinity, then what will happen to the Wronskian? The Wronskian will have the first column going to 0. Therefore, the second column, y2 and y2 prime, must blow up to infinity. Otherwise, how can the Wronskian remain non-constant? If one solution decays to infinity along with its derivative, that means that the column y1 prime goes to 0 as x goes to plus minus infinity. Therefore, the second column must actually grow exponentially fast. Otherwise, the Wronskian will not be a non-zero constant, it will become a 0. And that will be a contradiction because we have taken two linearly independent solutions. Okay, so one thing is certain, this equation cannot have two solutions in the Schwarz class. Only one of the solutions is going to be in the Schwarz class at most. Of course, is there such a solution? That's a question that we need to still answer. All we have seen is there is at most one solution in the Schwarz class. Let us proceed formally and let us take the Fourier transform of 4.15. What happens when you take the Fourier transform of 4.15? Fourier transform of y double prime. Fourier transform of y double prime is minus chi squared times Fourier transform of y. What about the Fourier transform of xy? Fourier transform of xy is minus 1 upon I dd chi Fourier transform of y. So two minuses, both of them go away. I have chi squared y hat plus 1 upon 3i dy hat by d chi equal to 0, which is equation 4.16 presented in the slide. This is a first order linear homogeneous ODE. So we can immediately integrate this by very elementary methods. And let us write down the solution. The solution is immediately written down. Y hat is exponential of I chi cube. Now I am ignoring the multiplicative constant because if y is a solution, then constant times y is also a solution to the Aries equation. So I can ignore the multiplicative constant, and we have y hat equal to exponential of I chi cube. Now we should proceed in good faith and go and appeal to the Fourier inversion theorem. So we should recover y from y hat using the inversion theorem. Again, there is going to be a 1 upon 2 pi factor in the inversion theorem, which I am going to ignore, and I am going to get y of x equal to integral over r exponential of I x chi plus I chi cube d chi, equation 4.17 that you see in the slide. Alright, now the exponential should be written as a cosine and a sine. Exponential of I x chi plus I chi cube will be cosine x chi plus chi cube plus I times sine x chi plus chi cube. The sine term is an odd function, so it's supposed to drop out, and so what we are supposed to get is a cosine integral 4.18, displayed equation 4.18 in the slide. Y of x equal to integral over r cos of x chi plus chi cube d chi. So far we have obtained an integral representation for the Aries function. There are a couple of very tricky questions that we must answer. We have assumed that the differential equation has a solution in the Schwarz class, or at least a Fourier transformable solution, and we arrived at this equation 4.18. So the derivation of 4.18 is suspect because we have made an assumption that the solution in the Schwarz class exists. The second thing is that we could say, well, somehow we have arrived at this integral formula. Though the derivation may be suspect, we can directly try and verify whether 4.18 satisfies the differential equation. Maybe we can directly use 4.18 and check that it does indeed satisfy the differential equation. But there again we have a problem, because when you try to differentiate 4.18, whether I can carry out the derivative under the integral sign, that's suspect, because the integral 4.18 is conditionally convergent. It's a conditionally convergent integral, and so first of all, it's not even clear whether it even converges. That has to be settled. Compare this 4.18 with the Fresnel integral, integral cos of chi squared. Integral cos of chi squared d chi, that converges. We saw that by integration by parts. Now this one is a slightly more complicated integral. We must first understand whether this integral 4.18 does converge at all. If at all it converges, it's going to converge only conditionally. Okay, so let us go ahead and check that 4.18 is a conditionally convergent integral. The idea is, first of all, it's an even function. So it's twice integral 0 to infinity. And then from 0 up to some r is a proper integral, namely the integral of a continuous function on a closed bounded interval, and so there is nothing more need be said about it. So we must look at the integral from r to infinity, say little r to infinity. And so in that region, let us make a change of variables, x chi plus chi cube equal to s. The function x chi plus chi cube is monotone increasing provided r is sufficiently large, and the derivative will be positive. And so the change of variables is a valid change of variables. The integral will transform to integral from capital R to infinity cos s. Okay, let's go back to the integral 4.18. X chi plus chi cube has been replaced by s. So the integral is going to become integral of cos s d chi by ds ds. Okay, so but what is d chi by ds? D chi by ds is 1 upon ds by d chi. What is ds by d chi? 3 chi squared plus x. So that's what you see in the denominator. So that's how we get 4.19. So we made a change of variables and we reduced the integral 4.18 to the integral 4.19. Now integral 4.19 is slightly looking better because we've got a denominator which goes to infinity. So chi of course is a function of s. And obviously this function of s, chi as a function of s, goes to infinity as s goes to infinity. Look at the equation, x chi plus chi cube equal to s. If s goes to infinity, then chi has to go to infinity. So now let us integrate by parts. Let us write cosine of s as dds of sine s. And let the derivative shift to the other factor, namely 1 upon x plus 3 chi squared. It's going to become 1 upon x plus 3 chi squared the whole squared. And then it will be 6 chi into chi prime. But again, chi prime was what? 1 upon x plus 3 chi squared. So all in all, you get 4.20, namely 6 times integral r to infinity chi of s sin s ds upon x plus 3 chi squared the whole cube. Now I have ignored the boundary terms coming from integration by parts. Those boundary terms will be perfectly in control. Some of them will be constants coming from the lower end of the integral. Others will go to 0 pretty quickly. So there is no problem with the boundary terms. We have to simply deal with the integral that is displayed in 4.20. Now that looks much better because let us see how does chi behave as a function of s. You see, we have the unpleasant job of expressing chi upon x plus chi squared the whole cube in terms of s. Now this is going to be a really unpleasant job, and we would have to do this if we want the exact value of the integral, but we don't want the exact value of the integral. All that we are investigating right now is whether or not the integral converges, and for that purpose we have no problem. We need just an estimate, not an exact evaluation. So we should not solve for chi explicitly in terms of s, that's too much work. But let us look at this equation. What is the basic equation connecting s and chi? X chi plus chi cube equal to s. So now look at x chi and chi cube. Chi is going to become large and the x chi is practically can be ignored, and so the chi is going to behave like s to the power 1/3. If chi behaves like s to the power 1/3, then chi squared behaves like s to the power 2/3, and x plus 3 chi squared the whole cube behaves like x to the power 2/3 the whole cube. So it behaves like s squared. So we are in a very good position. We are ascertained that the integral 4.20 converges absolutely, and so the original integral converges, but the original integral converges conditionally. Now we need to show that the integral 4.18 does indeed solve Aries equation. Why? Because the derivation of this was suspect. As observed earlier, differentiating under the integral sign is not going to be easy to justify, but the moment you differentiate under the integral sign with respect to x, the chi factor is going to come out. Already the cos x chi plus chi cube doesn't have good decay properties. It doesn't decay, but now we've got an extra factor of chi and the thing oscillates with infinite amplitude. So we are in serious trouble if you carry the differentiation under the integral sign. So we need to resort to a totally different technique, namely the technique of shifting the contour of integration into the complex domain. This is a technique that you're probably seeing for the first time here, but this is going to be useful in many other situations. Okay, so let us see what this idea is of shifting the contour of integration into the complex domain. Now look at this 4.18. There's a cosine term. I can throw in the sine term because sine is an odd function. I can write as cos x chi plus chi cube plus I times sine x chi plus chi cube. No problem. All in all, I can write it as exponential of I x chi plus I chi cube as I had earlier. Now I complexify the variable chi and I replace chi by z. Z is a complex variable, and now I look at the entire function f of z equal to exponential of izx plus iz cube. This function is complex differentiable on the entire plane, namely it's an entire function. Now what are we going to do? We are going to integrate this function along a rectangle. Rectangle with vertices r plus I eta, minus r plus I eta and minus r. At this juncture, you must go back and revise our derivation for the Fourier transform of the Gaussian. We are given the two different proofs of the Fourier transform of the Gaussian. One of them used complex analysis, and the complex analysis proof you must go back and revise before proceeding further with this. You'll get an idea as to what's going on. So now this rectangle, so let us look at the base of the rectangle. The base of the rectangle goes from minus r to plus r, and ultimately r will go to infinity. So z will simply be chi. So I just replaced z equal to chi plus I eta. I complexified the chi variable. I replaced chi by chi plus I eta equal to z. So along the base of the rectangle, eta is 0. So I get z equal to chi, and when r goes to infinity, I will get the integral that I want, namely 4.18. Okay. Now, show that the integrals along the vertical sides v1 and v2 tend to 0 as r goes to infinity. This is exactly the situation that parallels our earlier discussion about Fourier transform of the Gaussian. Over there also we integrated over a rectangle, and the integral over the base of the rectangle gave us the integral that we wanted, and the integral over the vertical sides go to 0 as r goes to infinity. This is something that you need to check. Now let us see what happens to the integral along the top edge L2 of the rectangle. Along the top edge of the rectangle, z equal to chi plus I eta. Chi runs from minus r to r, and eta is fixed. And so let us take the absolute value of what we are trying to integrate, namely mod of x of izx plus iz cube. So mod of x is the same as x of the real part. So what is the real part of izx? It is minus x eta. Remember, z is chi plus I eta. So I chi x should be ignored, and minus x eta becomes a real part. Now look at z cube. Z is chi plus I eta. So z cube will be chi cube term. So, but there is an I chi cube. You ignore that. Next term, 3 chi squared I eta. And then there is an I in front of it. So minus 3 chi squared eta. So that is important. The third term is what in z cube? 3 chi I eta squared, but that's real, and there's an I in front, so that term has to be ignored. The last term is I cube eta cube, and already there's an I, so I to the power 4 eta cube. So there will be simply eta cube. So we see that the mod of the exponential is x of minus x eta plus eta cube minus 3 chi squared eta. We are in a very comfortable situation because we have an exponential of minus 3 chi squared eta, and chi is going off to infinity, eta is fixed. So we can perfectly go ahead and we can compute, or rather we can estimate the integral. So we get the estimate integral over L2 x of I xz plus iz cube dz less than or equal to x of minus x eta plus eta cube into integral minus r to r exponential of 3 chi squared eta d chi. And the integral converges absolutely. So there is no problem with the top edge. Now let us appeal to Cauchy's theorem. Integral of an entire function along a rectangle must be 0. So integral of fz dz along L1 plus integral of fz dz along L2 plus integral fz dz along V1 plus integral fz dz along V2 is 0. But integral of fz dz along V1 goes to 0, integral of fz dz along V2 also goes to 0, integral fz dz along the base gives you the integral that you want, 4.18. Remember, 4.18, that was the integral that we wanted. And the integral along L2 is an absolutely convergent integral and a rapidly convergent integral. So we are in a very good situation. One more thing, integral along L1 you go from minus r to r. In L2 you're going from r to minus r. So the orientation is reversed. So for the integral along L2 you'll pick up a negative sign, and so all in all, letting r tend to infinity, we get this following equation: integral minus infinity to infinity f of chi d chi equals integral minus infinity to infinity f of chi plus I eta d chi. In other words, we get y of x equal to integral minus infinity to infinity x of I x chi minus x eta plus I times chi plus I eta the whole cube d chi. Now we can differentiate under the integral sign because the integral converges rapidly and absolutely. And so when you differentiate y twice with respect to x, what you see under the exponential is exponential of ixz. So two differentiations will pick up a minus z squared. What I had done is I introduced a 3i factor in the numerator and denominator for convenience, and I pulled out the negative sign. And a minus xyx upon 3, I had just put it down as it is, introducing the 3i factor. And so all in all I get minus 1 upon 3i integral minus infinity to infinity 3iz squared plus ix exponential of ixz plus iz cube d chi. But now notice that we have got an exact differentiation. The expression under the integral is exactly dt chi of x of ixz plus iz cube d chi. Now because the exponential factor is rapidly decreasing and goes to 0 very rapidly as r goes to plus minus infinity, the boundary terms will go to 0 and the answer will be 0. And so we see that this expression y of x does indeed satisfy the Aries equation. So we have completely justified the derivation of equation 4.18. Now the question you would ask is, in your undergraduate courses you have done a power series solution of Aries equation. So what is the use of all this complicated mathematics? Remember that the power series method is an elementary method. It gives you the solution of the Aries equation as a power series that converges on the entire plane. But power series, they are algebraic objects. They lend themselves to algebraic manipulations such as multiplication of power series, differentiation of power series, term by term, and so on. But by looking at a power series, it's very difficult to understand information about the location of zeros, asymptotic behavior, estimates of the solutions. To get asymptotic behavior of solutions and to get estimates, you need integral representations. Integral representations are much easier to deal with when it comes to estimates, but they are not easy to arrive at. We have to use transform techniques to arrive at them, and that's exactly what we have done. The asymptotic behavior of Aries function is important in optics, and it is used to understand the behavior near caustics in geometrical optics.